And it
Good.
goes.
So what we're going to do today is topic 9.2. If you wonder where is 9.1, we have actually done that under SHM. It's the energy portion, the x equals to x naught sine omega t cos omega t. I hope that sounds familiar. Sounds familiar? Okay, good. You can see a few knots over there. So we have done 9.1. Now we're going on to 9.2. And I'm going to show you the IB way of deriving whatever we're going to derive very soon, and I'm going to show you the ASB way of deriving things. And I'm going to show you why is it that it's inadequate just to settle for the IB way of deriving things. There will be certain gaps in terms of prediction of the trend beyond the first point. So let's begin with what we're going to focus on today, which is diffraction. Single slit diffraction. Now the single slit diffraction, I think I've gone through with you before that. If you have a wave where the wavelength is very, very small compared to the whole, what will happen?
Diffraction.
Would it bend? Would it not bend? Would it bend a lot?
Bend a lot, very small.
You sure?
Yeah.
How about this case? This case?
Then won't.
This case, no bending?
Then
No.
So
It's
which
a line
of the
or
case, A or B is the one that doesn't bend? A is the one that doesn't bend, please get this right, yeah. Please make this, yeah.
Totally
And
forgot.
this, and then remember the in-between case, where in between A or B, where the size of the opening is somewhere in between, and then you'll get this. Okay? Not a very good drawing because I should have make a conscious attempt to make sure that the wavelength are the same. So make sure that you're drawing the wavelength are the same. Okay? So just to summarize, if the opening size is very big compared to the wavelength, then there is no bending. If it is approximately the size of the wavelength, it's 90 degrees bending. And then if it is somewhere in between, then it's some bending. Now the question is, I'm going to ask a question, a three-letter question starting with W.
why?
Excellent. Why? Okay, thank you. Now you give me job to do. I'm going to finish. I'm going to go on to show you mathematically why. Now this is the IB way. Okay? Or probably even the A-level way. So we got a slit over here. Now, I'm going to say something that you may like, why? But I'm going to explain to you why we do so. I'm going to cut the single slit into two smaller slits. Okay, two smaller slits. So let's imagine it as two sources over here. So let's call this slit wave D. So do you agree that the distance between the sources is D upon 2? Still good? Still alive? I hope you're not lost by now. If you're lost at this point in time, it's really quite serious. Okay, so D upon 2. Now we've got two sources over here, D upon 2. Do you agree that they interfere somewhere further down? Far down, on the screen or somewhere. Yeah? So do you agree that if I call this theta, now this is 90 minus theta, so this is theta. Okay? Therefore, the path difference, which is this segment over here, this is the additional distance that this wave travels, is equals to d upon 2 sine theta. Still okay? Now, do you agree that, therefore, if I were to find the position of the first minimum, which is destructive interference, the path difference should be lambda upon 2. Not lambda, not 3 lambda, not 2 lambda, not 1.5 lambda, but the first minimum, so it is lambda upon 2. Therefore, if I work this out, this is this one. And this is a very good prediction to the pattern. What you're going to see if you were to send waves in, you're going to see an intensity pattern that looks like this. The intensity falls off like this, falls off like this. And this angle over here, if you were to plot this at this angle, it is lambda. Or rather sine inverse lambda, which is a good prediction. But here comes the problem. Question number 1. Why do you cut it into 2 slits? Why not 3 slits, 4 slits, 5 slits? Because it's virtual slits, right? It is not physically 2 slits. Agree? So why not 3 slits, 4 slits, 5 slits? Question number 2. If you were to go for the other minimus, experimental result shows that this is 2 lambda upon d. The next one is 3 lambda upon d. If you were to go by this one, can you see that this will be 3 lambda upon d, 3 lambda upon 2. So by right, according to this will be 3 lambda upon d. Can you see that it missed out this portion? Understand? So you can see that, okay, it works for this, but it is not enough. It is not a robust enough derivation. So you should be very, very unsatisfied and therefore yearn to know more about how to derive the full formula using the complex number. You should be like having a boiling desire. Yes, I want to know more. I want to be confused. Yes. Give it to me. So, are you ready? Since you want it, I'll give it to you. But before I go on to the confusing one, let's take a look again. First of all, do you understand the derivation? Second of all, do you understand the inadequacy of this derivation? Take a look. Give me 1 minute. 30 seconds. Quickly take a look.
Why is it sin inverse? Isn't it just
Right. Because if it is angle theta, I'm plotting against theta. So if it is theta, then it should be sine inverse of this. Because it's sine theta equals this. But usually when we're talking about light, say for example, light, the wavelength is small. So usually sine theta equals to lambda upon d is much smaller than 1. So usually we can say, we can make this approximation. If theta is in radians, then we can make this. I don't know whether you learn Maclaurin expansion or
No.
theta minus theta cube over 3 factorial plus theta 5 over 5 factorial. So if theta is small, then this all these terms cancels off, giving you this. Okay? Good tool to use.
So why is the graph like that?
Why is the graph? I'll experimentally prove that it is this shape. You'll see a bright band in the center, and then you'll see small little bands inside. Cool. So everyone okay? How to derive and why is it inadequate? Cool. Before I jump into the possibly, actually most likely confusing one. Can I? Okay, I'll probably leave this here, then I'll move on to here. Okay? Now, remember this thing? Our good friend? Yeah, remember? So, remember that if I were to cut this into not 1, 2, 3 slits, but n plus 1 number of slits. N plus 1 slits. You okay? Can you see that if it is n plus 1 slits, that means the separation over here will be d. If this whole thing is d, then this will be d divided by n. There will be n separation because you have n plus 1 slits. Cool. Therefore, the phase difference between adjacent wave over here, if you refer to the previous the way where we derive things, the phase difference between the adjacent light that comes out of it and the angle theta will be equals to 2 pi upon lambda d upon n sine theta. This is the delta x or the path difference. If you're wondering where this comes from, it's actually from here. It's the d sine theta. Just that just now it is the separation between the sources is d upon 2. Now the separation is d upon n. Which is the n be n first. We haven't given n the value.
So why is it?
Phi is the phase difference. Yes. It's 2 pi times the path difference divided by wavelength.
Why is it d over n, not d over n plus 1?
Because if you got 10 folds, say for example, let's say you got 4, 1, 2, 3, 4 slits.
4 plus 1.
3, 4. 1, 2, 3. So you got 4 slits, you got 3 separation.
Oh, okay.
Okay. So still okay now? Therefore, we're going to park this for a while. We're going to call this whole thing phi first. So the light that comes out from the first slit, you have this representation. The second slit, that's what is first, second one, then you have x naught e to the power I omega t plus phi, and then to the xn, which is x naught e to the power I omega t plus n phi. So what we do is that we add them up. Okay? So x equals to x resulting equals to x1 plus x2 plus x3 plus equals to x naught e to the power I omega t. Still remember your ABGB? ABGB? Remember that A plus AR squared plus to R term, N term, the sum is equals to A times 1 minus R over 1 minus R to the power N. Or, yeah. 1 minus R to the power N.
That is it.
I haven't got to the point of infinity yet, but this is sum to N terms. Do you follow? Okay. So therefore, if I were to put this, this would be 1 plus e to the power 5 plus e to the power 2 phi, and then plus e to the power I n phi. Now if I apply this formula, the total will be equals to e to the power I omega t, 1 minus e to the power I n phi over 1 minus e I phi. Now this is the part where I'm going to do a little bit of math voodoo. Okay? Then, now, which is equals to e to the power I omega t, e to the power I n phi upon 2. I did this last time. Do you remember? Yeah. I basically just, if you take this, multiply by this, you get this. If you take this, multiply by this, you get this. Actually, it's this.
No, it should be just. Yeah, one you get this.
Okay, hang on. Does it matter if I were to just take this, and this? Correct. Okay. So I take this.
But then you will get minus
this.
Shouldn't get minus that also.
Which one? This one times this one will give you 1.
Yeah.
This one times this one will give you
Will it be minus I?
plus. You want plus because this half, you want it to be 1.
Oh.
Yeah. Still okay? Now, what is this from the complex numbers, which I'm sure that you are very proficient right now? Conjugates, yes, right. At this point of time, probably can I have you to just tip the camera a little bit towards here? You might miss out a little bit on this side. So I want this to be captured. Is this captured?
Yeah, it was fun.
It is. Okay, fine, good. Now, can you see that this will be x r equals to e to the power I omega t, e to the power I n minus 1 upon 2 phi multiplied by sine of n upon 2 phi divided by sine phi upon 2. You learn this in complex numbers, no?
Yeah, but
Like
this.
e to the power I phi plus e to the power minus I phi with a sine of thing. Yeah? So this one x r will be equals to, am I just enjoying myself counting? It takes time to sink in, no worries. Then multiplied by sine n upon 2. Now you plug in the phi. 2 pi upon lambda d upon n sine theta divided by sine of phi upon 2, which is going to be pi lambda d upon n sine theta. Quite a nice thing. Now this will give you e to the power multiplied by sine pi d sine theta divided by lambda divided by pi lambda d sine theta times n. Now hang on, why is it that I can remove the sine from the bottom? Because remember, if I were to have a sine theta that is small, which is small because n is going to be a big number, I can approximate it to just this thing over here. And I multiply the n to the top.
But then for the top one, since it's not together, then you can't then.
Actually you can, because if actually I miss out x naught along the way, because if you have an x naught, if you have an x naught, and this one multiplied by x naught, n times x naught is actually the total amplitude of the wave, which is the, it doesn't matter, but n times the, because n is the number of slits, x naught is the wave, the amplitude of each of the wave over there. So if you sum up the amplitude of each of the small wave, it is actually the amplitude of the original wave. Yeah? Now what you have over here, can you see therefore the amplitude of the resultant wave is dependent on this factor over here. I want you to take a look at two things. First thing, when is this thing 0? The numerator or the denominator 0? Numerator. When is the numerator 0? You look at the sign, I hope you still remember your sign graph. When is the unit cut axis? When eta equals to?
0,
Pi, 2 pi, 3 pi.
Yeah.
Now if you let this be equals to say 3 pi, say for example, or 2 pi, can you see that pi d upon lambda sine theta equals to 2 pi? You cancel this away, you'll find that sine theta is actually equals to 2 2 lambda upon d. Can you see that you finally get something that is missing over here?
All that.
2.
You're going to get all your lambda upon d, 2 lambda upon d, 3 lambda upon d, everything will come out. This is the most general derivation. And if you, in fact, if you plot this function over here in terms of theta, you're going to get this.
So you get the rest as well.
Graph over here. Yes, correct. You're going to get whole pattern.
Sir.
What on earth?
Wait, sir, 2. Why?
Okay. Okay, this one. Okay. The idea is that because ei theta minus e minus I theta is equals to cos theta plus I sin theta minus cos theta minus plus I sin theta. So this cancels out, which is actually equals to 2I sin theta. Then you divide by 2. So sin theta, I sin theta is equals to half of e theta minus e minus I theta. But the I will go off anyway because the top and bottom we do the same thing. The 2 i's will cancel. This one. So this one will become sine of this thing over here. In fact, it's 2I sine of, if you take a look, this one is actually equals to 2I sine of whatever that's over here.
So you're using the equation for within the bracket or between?
Within the bracket, and this one, sine of this one. That's why you see I brought this out. Oh. Okay, what I'm going to do is, I'm going to write it meter. Okay, I'm going to write it meter. But I need the whole board, that's why I only got that part to squeeze. What I want you to take note of is, are you okay with this? You okay with this? It's probably take 30 seconds because I can see some very concerned. Actually, it's okay. After that one, okay already. Actually, it's okay. After that one, huh?
No, oh yeah, I was okay with that.
For your syllabus, actually for your syllabus, you just need to know this. But I'm sure that as very excited and enthusiastic ASB students, you're definitely not satisfied with what is inadequate. And you have to know what is inadequate.
Refund for Derek that came out.
Sorry?
Refund that came out and everyone died.
No, this just cannot come out.
You get banned. You'll be banned from sending questions.
What I'll do is I later on when I switch off the recording, when I finish with this thing, I'll rewrite the whole derivation in the meter form and the full form so that you can copy down from it. And I think I was very squeezed over there, so I had to jump in the sense.
Yeah, that's why.
Okay, so now let's take a look at what's the implication of this, yeah? And it has to do with resolution. So we're done with the first part actually, the diffraction, which is you need to know the angle for the first minima is actually lambda upon d. How does this tie back to what we went through just now? When the wavelength is very small, it goes like this. Why on earth does it say this? How does sine theta equals to lambda upon d tells us this, right? Because this is single slit, we've got the equation for single slit diffraction. So how does the equation tells us what is, explain what is happening in real life? Now can you see that when the size of, when d is very much bigger than this, sine theta, which is equals to lambda upon d, is approximately 0. So theta is approximately 0. Now what does theta approximately 0 means? It means that the first minima, because theta over here is the angle to the first minima, it means that the angle to the first minima is directly over here. Directly opposite. So you form a minima directly opposite means that there is no spreading. Now take a look. When sine theta is equals to lambda upon d and lambda is approximately equals to d, what is sine theta equals to? That's correct. And theta is equals to? Now what does theta equals to pi upon 2 means? It means that the first minima is formed over here because theta is measured from here. So what does it mean when the first minima is formed over here? It means that the wave spreads all the way to here.
So it goes on.
Exactly. That's the physical meaning of theta being at pi upon 2. Now what if lambda goes even smaller than d? Oh, sorry, what if d goes smaller than lambda? Yeah, because this is d equals to lambda, so if wavelength like this, yeah? What if d goes even smaller than lambda? Goes backwards. Magnus effect. Ah, brutally. No worries, it's still 90 degrees. It doesn't go backwards. Yeah. Relax.
I was like, what?
Goes backwards. Okay? Now you understand the mathematical derivation and how it gels with physical observations.
Because the slits are in this, right? So the light can go beyond.
It can't go beyond, the wave can't go beyond 90 degrees.
Yes, sir. Look,
Maybe you're trying to
the graph will look like what?
Sorry?
The graph will look like what?
The graph is always like this, it's just the value of it. What's the value of it? You just spread out more and more and more and more as your D gets smaller and smaller.
What?
Yeah.
Just tell me.
In extreme case, it will look something like this.
Isn't this
So it's
just
almost constant throughout the stream.
the 90-degree case?
When you stretch it out so far that it's almost constant. But the catch is always when you spread out so much, this will be very small and then it will go down because it's spread over a long time.
So you still see the strips?
No, then how
The strips, you mean the minimums?
Yeah.
The minimums will appear at 90 degrees, then it just means that it doesn't exist. Okay? Can I? Okay, good. Let's try a simple question. And then simple one, really simple. No worries, it's very simple. I will rewrite everything neatly over here, no worries. After I finish this section. Okay.
So I just question.
Yes?
I just a question.
What's the question?
Why so easy?
600 nanometers, 0.5 mm. 0.4 mm. And this is 100 meters. Find the size of this. Find first minimum. And 69. Give me a shot. Simple one. Aditya, you got it.
Is it just how you said that when lambda is bigger than d?
When lambda is more than d, is what? Oh, you mean in case that lambda is more than d, that means it gets even smaller than lambda. Yes?
Yeah, then the wave, you just say it travels the same way as when
It's
it's.
not. It's circular.
But then why is that? Like, wouldn't there be no angle?
There's no solution there. Yeah. So it cannot go beyond that, so it just stays as is.
So there's no proof for it.
Well, it's observed that it behaves like this.
Oh.
So, yeah.
I will prove it.
Yeah. You never know. Probably you can try. Probably there is some strange phenomenon that we haven't got to understand or know of. You never know. Or phi is basically 2 pi upon lambda times the path difference, and the path difference is this portion. Remember path difference? This just now when we derived, it is if this is d, then this is d upon 2, and the path difference of this wave is d upon 2 times sine theta. So it's almost the same form. You take d divided by the number of slits times sine theta. We only go for first minimum because if the light over here forms a patch, this is the boundary of the first minimum. Back to your question. Yeah, so it's d divided by the number of slits, which is n times sine theta. So which is in this form, d divided by the number of slits times sine theta. That's the path difference.
I don't know.
2 pi over lambda, that's the phase difference. So remember the last time we were talking about phase difference, where you have 2 pi is to one wavelength, and angle is to the path difference, which is, let's call it x. So then you work out that theta is equal to 2 pi times x upon lambda. The x in this context is your path difference. Yeah. So I'm converting a physical length into an angle.
So for this lesson, is it the IB thing or the ASB thing?
This is IB. The only part that is, whenever you see I omega t means ASB. Whenever you see phasor diagram, ASB. Yeah? Seriously, since you're ASB. Oh man, yes, advanced, very advanced.
I should have just wanted to use
Basically, the idea is that I'm showing you that things spread out. No matter what you do, this is physics. There's nothing you can do about it. It just spreads. So the theta is equals to lambda upon d, which is going to be equals to 0.604 minus 7. Right. Then minus 4 is going to be 410 60 divided by 415. Radians of this is in radians. Now, how do you find the physical length then? Remember your circular measure? S equals to r theta. Remember? Theta S r.
Oh, because you assume they just express out one.
Yeah, because the angle is very small. And no, because the angle is very small, this is almost straight. So if you work it out, you'll find that the patch over there is 3 meters big. 3 meters big. The D is 3 meters. Okay, I did some mathematics calculation. I might be wrong. 1.5. 1.5. Do you multiply by 2? Because it's what you found is the radius.
Half.
Oh,
Half
yeah, what
of
you
it.
found is the angle theta here. So you need to times 2. That's the angle to the first minimum. So I got 30.
Yeah, I got 30.
Huh? Hang on. Did I get
30.
30 or 3?
Thir-
3, sorry. 3. I took this angle times 2. Then times 1000.
There's either
3 meters.
Yeah.
But do you see the implication of you got such a
Oh,
small
it's
hole,
just-
0.4
okay, get it.
millimeter, you know how small it is at all? You shine light through that hole, inevitably it will be 3 meters big just 1 kilometer away.
Okay.
Which means if you take a laser pointer and shine at the moon, for whatever reason you want to do that, actually the beam at the moon's end covers the whole moon probably. Yeah, it spreads and spreads and spreads.
So can you make it spread inwards?
You want to converge unless you put a big lens. Yeah. Unless you put a big lens, but how are you going to do that? Put a series of lenses or what? There's nothing much you can do unless one way is if you want to reduce the divergence, the only way is to make a big. You make a big laser. The bigger the laser it is, the bigger the aperture, the better you stay straight. And that's the reason why telescopes, I'll explain to you why telescopes, they always have big diameter.
But so weird. How can it move out like in a spherical field?
It's just the way light interacts with edges. As it spreads out from the edges.
Because the wave.
Now think about this, you do know that light is made of particles as well, right? Why on earth, from the particle perspective, does it? Right? You open the door, people just rush out. Why suddenly people...
Magnus effect.
Magnus effect, Bernoulli. We know.
If you don't know it, it's
That's everything Magnus.
there's a Magnus in my class.
Yeah, of course.
And his name is
Interesting.
So, what is the formula like that?
You mean this one?
Yeah, why?
Oh, didn't we just derived just now that the angle to the first minima is this one? Yes. So why is this the first minima? Remember that light spreads as it comes out? Yeah. This is the position of the first minimum. Remember just now when I drew the intensity pattern? It looks like this. When I have a small aperture over here, when light travels outwards. Now what this means is that this is bright, this is dark, which means that is the boundary of your patch. Oh, okay. Use sine theta and theta interchangeably because in this case the full formula should be sine theta as you have seen just now. But very often we use sine theta approximately equals to theta, therefore is theta equals to lambda. Now you have seen for yourself, most of the time, the wavelength that we use of light is going to be really small. Yeah, and the whole size is usually of a many order bigger. So that's why lambda 1D is usually very small. So we can make this approximation. But if you want to really go by the correct form, it is this one. Not theta.
So, what is it lambda instead of?
Why is it lambda instead of?
Half lambda.
Oh, remember if you go back to the derivation, we split the single slit into two smaller sources. Right? So let's take a look, yeah? This one, you split into two smaller sources, so this is D upon 2. So the path difference between the two waves is D upon 2 sine theta equals to lambda upon 2. So the 2 cancels. That's why. You must be very careful, yeah. Since you asked, it's good to reiterate that. Yeah. Because in another derivation, you're going to see that sine theta equals to lambda upon D becomes the maximum. So it's good that you asked. So we must be very clear. For single slit diffraction pattern, sine theta equals to lambda upon D is for the first minimum. Still alive? Okay, probably I will just stop here for a while before I go on to the next part.